Welcome to video number 2 in Advanced Fluid Mechanics. So here's a summary of what I'm going to be covering in this video. And basically we're starting here with an introduction to some mathematical notation that we commonly use in Advanced Fluid Mechanics. I'll also do sort of a short example in section 1.5 that looks at how we use this mathematical notation to figure out the force that's acting on a surface. And I want to mention one thing too before we get started here. There is a textbook that I use when I teach this course, so I'll show it here. And this is just the cover for the edition I have now, but really any edition you can get would be fine. So it's called Fluid Mechanics, and I don't follow it exactly. I don't cover every section, and I don't go in necessarily the same order, but for the most part, the majority of the material that I cover in this course is covered in this book as well. So if you'd like to have a textbook as you go through this course to help you learn this material, this is the one I'd recommend that you follow alongside these videos. Okay, so we're starting here with section 1 that I've called Cartesian Tensors. And basically what we're going to be doing is becoming familiar with some of the mathematics, or more specifically, like the mathematical symbols or the mathematical notation, we could say, that's commonly used for advanced fluid mechanics problems. So we could really think of this as like we're learning the language of fluid mechanics. And in this way, as we come across other people's works or looking through problems in advanced fluid mechanics, we'll know exactly what they mean, what they're trying to say. So in 1.1, it's scalars, vectors, and notation. And so we're going to use what's known as index notation. And we're going to follow what's called Einstein summation convention, which basically says if an index appears twice in one term of an equation, summation is implied. So below here, I'll do a really quick example. So that means if I write A subscript I, the I is the index, right? And it's repeated, it appears twice in this term. So what that means, when I write this equal sign here, but with 3 lines, that means is defined as, and that actually means we're going to do the sum of AI, and we're summing that over I. So what that looks like is A1 plus A2 plus A3. And apparently when Einstein came up with this, he joked to a friend that he'd come up with this new set of rules for writing equations that saved him from having to write the summation sign all the time. So this is definitely a more compact, like a neater way to write these equations. Okay, we also say in a term, one index can appear once, and we call that the free index. And it can appear twice, which we've just said is summation, but not more often than that. So an example of that, and I'll use a slightly different color, I could have this expression here. Okay, now our free index is the I, and then we have a repeating index, which are these j's. So if we look at this term here, right? So that term will have a free index of I, but then it has a repeating index of j, but it appears 3 times, right? 1, 2, 3. So we know that this is no good. This breaks our rules, so that can't be true. And this is a good way to check, right? Like if you see equations or you're working with equations and you have an index appear more than twice, you know there's something wrong. You know there's a problem with it, right? So you got to go and find the problem and fix that. And then finally, we say the indices in all terms of an equation must be the same, and all terms must have the same number of free indices. So an example of that in a different color down here. Give a few little examples here. So in vector notation, what I'll do for that in this course while I'm writing it out, if I'm in vector notation as opposed to index notation, what I'll do is write the vectors with a line under them. Okay, so if I want to say that the vector A is equal to the vector B, I can write it that way in vector notation, or in index notation, I could write AI equals BI. And so to check our rule here, our third rule, the indices in all terms must be the same. So they are the same, right? So the AI and the BI, they both have an I index, and they both have the same number of free indices. So the I matches the I. What we couldn't do is we couldn't say AI equals BJ. Okay, they're not the same. So that would immediately tell us something was wrong there. So that can't happen. We also can't have a different number, right? We can't say AIJ equals BJ, let's say, because we have 2 on the left and 1 on the right, so that we would know that would be a different number of indices. And we could also look at something like this. So we could say like T IJK UK plus MIP. Okay, now if we look at that, they have the same number. So this term here on the left has an I and a J as the free indices. We don't include the K because that's a repeating index. And this term has an I and a P. So they both have 2, but they don't match, right? So in this one, right, the K's are repeating. So we don't include those because that's a summation. But the I and the J, right, don't match the I and the P. So this also, that's no good. So that would immediately tell you something was wrong there in that one as well. Okay, that's the basics of index notation. And as I go through this, another comment I'll make is that you may have seen some of these things before or not other things. And there isn't really an order to how I'm laying this out. I'm going in sort of the order that I was taught it. And what I've done here is just to compile a whole bunch of things that I learned throughout grad school or throughout working with advanced fluid mechanics problems that I find useful to know. Okay, so I've compiled this from a few different sources. So you may see things you've seen before and some that you haven't. And so what we're doing here is just making sure we cover everything. So as then when we go further in the course, we're all speaking the same language. Okay, now we'll talk about a Euclidean basis. So this is an orthonormal vector basis. We'll look at 3 dimensions. What I'm going to do when I write an R with the 2 lines there is I'm kind of denoting that it's like a bold R, okay? Because it's tricky for me to bold it as I'm writing, not using the computer text. So what I'll do is kind of do that double dash on the R. So that's R3. So that's 3 space. So we have 3 dimensions. And Euclidean basis would be E1 would be 1, 0, 0. That's the vector there. E2 is 0, 1, 0, and E3, 0, 0, 1. And I'll just use curly brackets for those vectors there. We would also maybe have seen that as EX, EY, and EZ. So this is another good example to sort of relate how that free index, the 1, 2, 3, if I is 1, 2, 3, we could also think of it as X, Y, Z. Same basic idea. And then we would have our B vector, right, would be B1, E1 plus B2, E2 plus B3, E3, right? So each component of our vector with the basis there, all that added up together, it gives us our total vector. But we can see that this is actually the sum, if we go from I is 1 to 3, of BI, EI. That's like a shorter way to write it. But of course, we're in the Einstein summation convention. So actually, if we just write BI, EI, summation is already implied. And so that's a shorter way to write it there. And just a quick note again, you see when I write the E's, I put that little line through it. Again, that's just my way of denoting that it's bolded, right? If I used like a thicker pen here, it wouldn't really be as clear as I would want it to be. So that E with sort of the line through it is just like a bolded E. Okay, now let's look at a few more things here. Many of these things are much easier to write with index notation. So we'll first look at the scalar product, which is also known as the dot product. So in vector notation, that would look like this. But we see that what we're doing is we're summing over each of the indices. So in index notation, we may recognize that we can actually just write this succinctly like this. The Kronecker delta is next. This comes up quite a lot actually, depending what specific fields you work in. And the Kronecker delta, denoted as delta with the indices I and j, that's going to be a 1 if I equals j and a 0 if I is not equal to j. So let me show you just one way we might use this here. If I said the scalar product of 2 of my basis vectors, so the dot product there would be 1, only if I is equal to j, and it's going to end up being 0. Right, if I is not equal to j. So actually, EI dotted with EJ is the same thing, right, as the Kronecker delta. Okay, so if I then write a dot product, we can see something cool here. as we just saw previously, I can denote B as BI EI dotted with CJ EJ. We rearrange that slightly. And this portion, as we just saw, we can write as the Kronecker delta. So we have BI CJ. And then we'll stop there for a second. And now I'm going to show you a change of index, and then we'll come back to that to see what this shows. So we'll do a little example here of what happens when you have the Kronecker delta applied to a vector in index notation. We'll see that it results in a change of index, and I'll actually show that out here. So what do I mean? So if I have delta ij and then uj, so what this means, because we have the free index I, and then we have repeated index j, so what this is saying is delta I, and then we sum over the j's. So let's write that out here, right? Now, by looking at this, we can see that the right-hand side, I'll write that as RHS, is U1, right, when I equals 1, because this is only a 1 when I equals j, like when they have the same index, right? And then if I equals 2, it's U2 because now, right, like this one that we just looked at would have a 2 and a 1, that would be 0. But this one here would be a 2 and a 2, so that would be a 1, right? So then we would only be left with the U2 term, okay, etc., etc. You can see where this is going, I think. So therefore, because the right-hand side is actually ui, we can just write this as like delta ij uj equals ui, right? And this is one of the most powerful things of the Kronecker delta, is it's actually a change of index. When you have it in an expression, what it can do is it can change one of the indices. And so if we go back to the example above here, right, we see from this line here that this is actually equal to BI-CI and BJ-CJ. We could flip either of the indices. And we know from what we've written above, right, we know that that's this dot product as well, right? So we've shown that BI-CI is equal to BJ-CJ. And both sides match because they both have a repeated index, so they're both scalars. And that, of course, is why this is called the scalar product, right? Because the result of the dot product or the scalar product is a scalar. And then one last thing on this slide here is the identity or the unit matrix, which I'll draw with like a bolded I. So I'll do the two lines again. And that is actually a matrix, right, of the Kronecker delta. Right? So anytime I equals j, so in the 1, 1 position, we have a 1, and in the 2, 2, and in the 3, 3, we have 1s. So you'll see the Kronecker delta written that way is same as the identity matrix. So that's a matrix form of the Kronecker delta from up here. 1 when I equals j, and 0 if I is not equal to j. And so just as a reminder, anything multiplied by the identity matrix is just the original thing again, right? So anything multiplied by the identity matrix is itself. So we could write it any which way, and we're always going to get a. A times the identity matrix equals A. Okay, now we're going to look at second order tensors. That's another thing that can come up commonly in advanced fluid mechanics, specifically because of the stress tensor, as we'll see later on. So second order tensors will have two indices. So in vector notation, I'll denote those with like 2 underlines, whereas a vector I did 1, right? Or I can write them as like a bolded capital letter, right? So I'll do the letter with this like extra line in it like that. And so what that means is like the vector A would have been like A1, A2, A3, but the tensor, the second order tensor is like this. Okay, so we have the two indices, and with respect to a base, we would write it like this. Okay, now we can apply a contraction. And so we'll look at what that is in index notation, where we can reduce the tensor rank. So in vector notation, we'd write it like that, but it's more clear to see that played out in index notation. What we would write is okay, so we have the free indices I and k and then the repeating index j there. So that results in CIK. And this is, if you can remember back to algebra too, when you multiplied matrices, we needed that middle index to be the same. And then if we have a second order tensor and a vector, it would look like this. And the free index is I, right? So that side would be the vector Ci. Now a transpose is really convenient to write in index notation. So if we were to write in vector notation AT, and we remember for a transpose we're exchanging row and column, right? So that, just remember, would be like this. A11, and then it would be like A12, A13. So it would be A21, A31, and you can reference the second order tensor above there to see how I'm taking the transpose by switching the rows and columns. If you look just there as a comparison, and then in index notation, we can write that like the transpose of ij equals AJI. Really easy to do in index notation, right? Okay, now we're going to look at what we mean when we say we have a symmetric tensor. So A is symmetric if the transpose is equal to the original tensor, or in our index notation, we would say A if Aij equals AJI. Then that's symmetric. An antisymmetric tensor A is antisymmetric if the transpose is actually equal to the negative of the original tensor. Or in index notation, if we say Aij equals to negative AJI. Okay, now let's look at decomposition. So if I say I want to decompose A, what I mean by that is that I can take Aij, and I'll just split it up and I'll say, okay, so that's going to be equal to half Aij. And then what I'll do is I'm going to add half AJI. I'm going to add another half Aij, and then I'm going to subtract half AJI. Now we see that that is still true because I've added half Aij, right, to give me the full Aij, and then I have this half AJI, but I've also subtracted half AJI, so that equals Aij. I have not left myself much room, so I will erase my circles and try to write this very small and maybe in a different color so it's more clear. So we say that this is equal to A with the one curl bracket like that, and then this portion here is A with the square brackets. That's how we denote that. And then we have the symmetric portion, which I'll make it clear is this one. So for the symmetric, let's bring us over here where we have a little more space. A, the symmetric part, equals to AJI, the symmetric part, which is equal to half AIJ plus AJI. And for some of these things, it's going to help to have some experience with these or play around with these. So I encourage you to actually, you can write out these matrices and prove these things to yourself, right? So when I teach this as a grad course, I'll have an assignment with this, right? And so the assignment is to sort of play around with all these things and convince yourself, prove them to yourself. It's actually kind of fun, to be honest with you. Now we have the antisymmetric portion. Let me use a different color. Maybe a purple would be nice. So the antisymmetric portion, which is this one, square brackets, and we have our definition above there. So that has to equal the negative, right, of a ji, which we have from above is actually half of a ij minus AJI. And again, I think proving that to yourself would be a fun exercise. So I will write now how we display this in vector notation. We would say I'll write it over here where there's still a little bit of room. Symmetric portion is equal to half of our second order tensor plus the transpose, right? Which is what we've written right below it. The curl brackets there are symmetric. And then for the antisymmetric, we'll use A, and that is half of our second order tensor minus the transpose of it. And so we see that I can write a tensor as the sum of its symmetric part and its antisymmetric part. Now let's look at what's called the trace of a tensor, which is actually just the sum of the diagonal elements. And so we would write the trace like this, TR for trace, and that actually equals AII. Really easy to write in index notation, right? And so we can see, for example, the trace of the identity matrix that we had before. We can actually write as delta II, because the identity matrix is the matrix form of the Kronecker delta, right? So if I were to write that as delta II, we would see that that would equal 3, because I would take delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is 1 plus 1 plus 1, and that is 3. Now we can also write the trace-free and symmetric part of our tensor, which is sometimes also called traceless, or the deviatoric part. Deviatoric you might see come up too if you're spending a lot of time with the stress tensor. You might see that terminology. So the trace-free part, we write like this. And we can actually see a property here is that if we put II that actually equals to 0. And that, again, I think you'll learn more. I think you'll get more out of this if you, as a quick exercise, show that to yourself. And then we can decompose again. So I will have the property that my tensor can be as follows. And the antisymmetric part. And that, I think you can see if we take this and plug it into here, right? You'll see that actually like this cancels this. And then we're left with our symmetric and antisymmetric parts, which we already know add up to give us our original second order tensor. So as I mentioned, that's a notation and a terminology you might see come up when you're dealing with the stress tensor, specifically for advanced fluid mechanics. And I don't know if it helps to see this written out, but I can also write out this one. So I'll show you why this is equal to 0. If we take this term here, our symmetric part as defined earlier is half, but we have the same index, so AII plus AII, which just equals AII. And we have this part where delta II equals 3. So we have negative a third times AKK times 3, right? So these two cancel out. So then we have AII minus AKK. That equals 0 because AII and AKK are the same, right? There's just the repeating index, whether you call it I or K does not matter at all, and no free index, so they would be the same and cancel. and leave you with 0. Okay, now I've called the next section more on vectors. So there's a bunch more things that I want to show you here. Specifically, it's showing you some of these things with index notation. I'll mix up the colors a little bit here so we don't get tired of seeing the same ones all the time. For the absolute value, I can write that as the square root AI. If I want the direction of a vector, I would divide it by A, and this would have n equals 2 square root of ni, which would equal to 1, the absolute value of our direction vector. So that's how we would end up with a direction vector, n sub I. For scalar product, just a reminder that it is AB cos theta. So if we have our vectors, let's say they're like that. Let's say that's B and that's A. Those are vectors. Then theta is the angle between them. We have something called a direct product, which gives us a tensor. So that looks like this. Right, and to make our indices match on the left-hand side and right-hand side, we have ij and ij. So that's why that gives us a tensor. We have the cross product, also known as the vector product, which in vector notation we write like this. We remember that C is perpendicular to A and B. In index notation, we could write it like this, with the Levi-Civita symbol. Cross product of AJ and BK would equal CI. And again, we check our indices to see that J is repeating, K is repeating, so we have free index on the left of I and free index on the right-hand side of I, so they match and everything's good. But what is this symbol here? The Levi-Civita symbol we'll define below, also known as the alternating tensor, sort of similar to the Kronecker delta in the way we define it. So we write it this epsilon with the indices I, j, k. So that's 1 if I, j, k equals 1, 2, 3, 2, 3, 1, or 3, 1, 2. It's 0 if any two indices are equal, and it's -1 if we have any of the other patterns of I, j, k, which are the 3, 2, 1, right? So not in order anymore. So 2, 1, 3, and the 1, 3, 2. And that's how that yields the cross product, right? We can also see the property that this will equal the negative of any of these being written with a different order of the indices, right? J, K, I. So we can substitute if we need to in an equation. I, K, J, and then, et cetera, et cetera. And we also have the interesting property, I'll write it like up here where there's space, is that epsilon I, J, K, epsilon KLM equals actually delta IL delta JM minus delta IM delta JL. And a check shows us that like this is repeating. So left hand side is IJLM, and that's IJLM, and that's IJLM. So that checks out. And then this is a relationship that I will definitely ask you to show in the assignment. And I recommend for those watching this that you plug something into that. Like this is really how you learn here, I think. Plug something into that so you can show that it's true, so you can prove it to yourself. It's much more powerful than just sitting here watching and trying to absorb it all. Okay, let's do determinants. So we write the determinant very similarly in vector and index notation. Okay, now depending on how many dimensions we have or how far we span our indices, we could write that I and j can go from 1 to n, let's say. For n equals 1, we have the determinant of a is just equal to a. For n equals 2, let's do it out here so that it's clear to see. So the determinant equals like this minus this. If you remember, it is A1, 1, A2, 2 minus A1, 2, A2, 1. And if n equals 3, and after I write all this out here, I'll show you that we can actually write this out in another way using our index notation and the things that we have defined today. It's already making us more powerful in our mathematics. Okay, so we take for A11, we sort of ignore those, and then the way we do that is we say A11 times -1 to the 1 plus 1, and then we take the ones that I didn't cross off in the bottom corner there and do it like this, plus, and then we take the next one, which is now 1 plus 2, A2, 1, A3, 3. So you imagine now I have sort of crossed off this, and now I have the other ones that are left not crossed off, and I do the determinant like this, and that's going to be an A2, 3, and an A3, 1 there, the bottom left. And then I would add A1, 3. Plus 3, and that's going to be A2, 1, A3, 2, minus A3, 1, A2, 2. Or I can say with a different color, I'm going to write in the top right now because I have so much space up here. We could say for a 3 by 3 matrix, how can we write this? We can say the determinant of A actually equals to 1/6 Ij K epsilon RS T A IR EJS A KT. And that is another way to write exactly what we have there for the determinant. So that's another way we can express the determinant, right? Using the things we've learned about today. The Levi-Civita symbol, also known as the alternating tensor, and our index notation. So that might come in helpful. We can also look at orthogonal tensors. So for an orthogonal tensor, the transpose is equal to the inverse, which it will help to write here. The inverse is the tensor that when you multiply it by the original, you end up with the identity matrix, or in index notation, Aij would be multiplied by Ajk, which is the inverse, and that would equal delta Ik. And in this case, the determinant of our orthogonal tensor would be equal to 1. Okay, now let's look at some calculus. And remember what we're doing here is just learning the language, right? So a lot of these things you may have seen before. So the reason I'm doing this is just to make sure when you see something written this way that you actually do know what it means, okay? Hopefully it's kind of fun. Like, I admit when I learned it was kind of cool to know that these like sort of weird symbols I was seeing, I actually did know what they meant, right? So we'll look at the del or nabla first, which is this. In vector notation. So then we have our gradients. So if we look at the gradient of a scalar, we can write it like this. Or this. Or even if we wanted to, like this. Okay, and remember that has an order of I now, right? That's a vector, right? We have that free index in there. So then if we take the gradient of a vector, we would have it like this. Or in vector notation, like this, it's now second order. And then if we take the gradient of a tensor, can't repeat that index, right? So we gotta go one more. That's going to be the gradient. written in vector notation like this of I, j, k. And then we have the divergence, and the divergence is actually the trace of the gradient. And the trace, we remember, is just basically the sum of the diagonal elements, right? So we write it like this. And in vector notation, that would be this. And then for a second order tensor, it would look like this. And that we would write in vector notation like this. And the curl, it's actually quite convenient to write the curl operator in tensor notation. We would use our alternating tensor, and it would just be written like that. Okay, now we get to look at eigenvalues and invariance. So we would write this as follows in vector notation, where the lambdas are the where lambda is the eigenvalue and x is the eigenvector. We can also write it like this. Identity matrix, or in index notation, and we haven't broken any rules because each term, right, the xj is distributed, so each term has a repeating j and a free index of I. And then for a non-trivial solution, we would have to have that the determinant of this part here equals 0. Okay, for the characteristic equation, we would have the following. Okay, and now we can look at these invariants here, and I'll just make a quick note here because it helps to be really clear that if we have this square of a tensor, we have to have this repeating middle index. Okay, and that's what that means in index notation. That's how you write this square, a second order tensor. So for our invariance, we would have and the corresponding eigenvectors form an orthonormal base in eigenspace as follows. Now we'll look at comma notation, which makes, believe it or not, everything even more easy. If I have a comma I like that, that denotes partial differentiation like that. So the divergence of a vector in vector notation looks like that, which equals this in index notation, or with comma notation and our repeating index, it's just that, which is more simple, right? And the curl of a vector, likewise, vector notation would be like this, or like this with our tensor notation, or even simpler with the comma notation, we would write that as u and then it's k comma j for that partial derivative. And now I think it's important to chat about some of the pros and cons of vector notation and index notation. So the nice thing about vector notation is the physical meaning of it tends to be clearer. We can sort of see immediately what it means, right? And there's no cumbersome subscripts. But the cons are that the algebraic manipulations are hard and cumbersome. We've seen how much more simple it can be to write the algebraic manipulations with index notation. And the order is important, and terms can sometimes be ambiguous, right? Because where the term appears, so like the order of the term in the equation matters, right? You have to keep track of that. Whereas in index notation, algebraic manipulations are much simpler and better defined, right? It tends to also be much more concise, right? So much shorter, simpler equations. The cons are that the physical meaning is not immediately clear. So you sort of have to look at it and see what each term means, right? Especially if you're using comma notation as well. And the cross product and a few other things require the cumbersome alternating tensor to be used. So on the whole, both really have their place. And depending on what we're doing in this course, I'll use both sort of interchangeably. But now anytime you come across them, hopefully you can switch between the two, and I'll set up some practice for this too in the assignment. Okay, now let's use what we've learned and start moving towards some applications. So let's first look at the force on a surface. I said here, if the 9 components, so T, I, J, so T is the stress tensor. So if the 9 components of the stress tensor are given with respect to a set of Cartesian coordinates, how do we find the force per unit area, Fn, with components, Fi, on an arbitrarily oriented surface with normal n as shown in the figure below? Okay, so this sort of arbitrary surface here is on a tetrahedron shape. And so here's one way we can solve this. So let's look at the net force F1 on this element produced by the stresses. So we would write it like this, that force per unit area times the area, dA, which we can break out further using the stresses acting in that same direction on each of the surfaces. We would write that like this. So T11 here acting on dA1. Likewise, T21 here on dA2. And you've probably got this now. If not, you can pause it and see if you can get the last one. We also have T31 acting in that direction on dA3. So the geometry of our tetrahedron means that we have the surface normal vector right there, right? So we have each of these surfaces are actually the components of the normal vector, right, times dA. That's how we would write that. Therefore, we can simplify our force equation even more. We can say F1 dA then is actually T11 N1 dA plus, and we go through them all, and 2dA, and this one, of course, N3 dA. Now we can divide out the dA's, right? And we have F1 equals T J1 N J, if we use our index notation, right? Summation is implied. Or more generally, right, for any component of our force, we can write it like this, Tji, right? N J. Okay, so there's index notation helping us to write out the force on an arbitrarily oriented surface. I'm going to box this too, because this is an important equation that we've just figured out. Can do a little example problem here too, just to make sure it's clear. So if we consider 2D parallel flow through a channel where x1 direction is parallel to the flow direction, the viscous stress tensor at a point in the flow is given as this tau equals 0a, a0, where the constant a is positive in one half of the channel and negative in the other half. So find the magnitude and direction of the force per unit area, F, on an element whose outward normal points 30 degrees from the flow direction. So we can see in the figure there. Okie doke, so we can apply what we just did. Now we need that normal vector. Let's do that first. So n is equal to, we can see from our geometry, just for simplicity, we're going to say that this angle we'll denote as phi. So that means we would have cos phi and sine phi are the components of our normal. right? Perpendicular to the surface. We'll see in the figure there. That right there. And then that equals root 3 over 2.5. Okie doke. Then our force equals what we just had. We can write it as tau instead of t if we want to. Tau ji, tau ij, doesn't matter. In either case, we're going to have 0a, a0 times our normal vector, which equals a over 2 and a times root 3 over 2, right? And that is a vector, so just to be super clear, that's an F1 and an F2. We are asked to find the magnitude and direction of the force per unit area. Okay, so the magnitude is this. Which, when we sub it all in, is the absolute value of a over 2 squared plus a times root 3 over 2 squared, all square rooted, equals a. Now we've denoted an angle here in the figure, so there's our f, right? And we're going to call theta that angle that it has to the surface, and we want to figure out what that angle is. So sine of theta is going to equal f2 over f. Do I need to show that? I guess. Why not, right? There's f and there's theta, right? So we would have, that's the one direction. That's the two direction right there. Okay, so we can sub in root 3 over 2 times a over the absolute value of a. And we also know that we have the cos theta, which is from the geometry that I drew there, right? It's actually just f1 over f, and that one is going to be half times a over absolute value of a. And then we could see from solving this that theta equals 60 degrees if a is positive, and theta equals actually 240 degrees if a is negative, from subbing in there, because then if a is positive, both the sine and the cos are both positive, but if a is negative, both the sine and the cos are negative. Okay, problem solved. We're going to finish now with two very useful theorems. Firstly, we'll look at Gauss's theorem. And Gauss's theorem here relates volume and surface integrals. So I've shown the figure on the right there. dv is the volume integral, dA is the surface integral. And so according to Gauss's theorem, we have this equation here. The most common form of Gauss's theorem is when Q is a vector. And in that case, the theorem, which is commonly called the divergence theorem, looks like this here, nicely written out in our index notation there. So there we have Gauss's theorem in index notation. Since the summation is implied, we have that this equals to this. Stokes' theorem, also very useful, relates the integral over an open surface that I've shown in the figure here as A to the line integral around the surface's bounding curve, which is denoted in this figure as C. And then given the directions for these vectors shown in the figure, Stokes' theorem would look like this, where we're relating the surface integral to the line integral. Okay, so in summary, in this video, we covered section 1 on Cartesian tensors, and basically we looked at some mathematical notation that's common in advanced fluid mechanics. Specifically, we covered index notation using the Einstein summation convention. We looked at how to write a whole bunch of different things and operators using index notation. We applied that to look at the force on a surface. And then we finished with looking at two powerful theorems, Gauss's theorem and Stokes' theorem. Okay, and that's all for video number 2. Thanks for watching.